our special guest, Lewis, who I'm going to hand over the presentation to, and I'll let you give a brief introduction and kind of tell us who you are, what you're doing, and what you're going to be talking about today. So,
Okay.
take it away.
Okay. Can I begin my presentation, my introduction right now?
Absolutely, Lewis.
Okay. Thank you, Travis. So I've come from RFThings. This is a small company. Yes, it's startup. So today I'm very happy to join with you in the happy hour, happy hour today. So first of all, I would like to present about my company. Yes, it is a small startup in Vietnam, and we have two team, two research team. One team is focused on embedded system and PCB layout and fabrication, and another research team come from France who work on antenna design and antenna measurement. My name is Louis. Normally in Vietnamese is Lê Huy Tịnh, but you can call me Louis. Yes, I'm co-founder of RFThings, and Mr. Fabian Ferrero, he is a scientific advisor and co-founder, also co-founder of RFThings. He lead of the friend team. Yes, work about antennas. So there are another guys. He lecturer of University Information Technologies in Vietnam National Universities. He is the development. He is the development lead. So it's a core team of our things, and we have another member who is the student and some engineer in Vietnam. So this is just just some information about our things, and then our service. We work about antennas. Yes, the antennas and some communicating device. Um, our mindset is antenna on system. How about this definition? Normally, when we try to design some wireless device, we begin with the schematic and then lay out it in the PCB, and then fabricate it. After that, we will find out some antennas on the market and try to connect it together via the by using a UFN cable or SMA connector. So, as our opinion, this way is not really affect. I mean, it not really it's not our best way, because when we design a PCB, we don't care about antennas. So after we finish the PCB design, we try to find a compatible antenna for this. It's really hard. Uh, and in another hand, when the guy who design antennas, he don't really care about what is the dimension of PCB and where is the connector, where is the point to connect with the antennas. So that's why in our company at the beginning we define the definition is antenna on system. I mean, when we normally the two research team, the antenna design and the PCB design is work together. At the beginning, we define the dimension of host device, and then we try to confirm where the fitting lies, where the point connected to connecting the to connect the device to to connect the PCB to the antennas. So from this moment we can to work in parallels. So uh, that is some brief definition about the antenna system. And then in Vietnam we have a small, not really small, but we have the the team who make the fabrication from the BCB, the SMT, and then we try to assembly with the antennas and packaging, something like that. Up to now, we have we can produce more series to the medium production, not really to mass production, but I think it's our future. And then our innovation driver is our device have a unique feature, and this is our service. And then today I would like to present also the our partnership come from friend. As I mentioned before, um, uh, one of co-founder of RFThings, he come from France. The professor Fabien Ferros, he worked in the LEAT laboratory. He is the laboratory of electronic antenna and telecommunication of University Côte d'Azur. So in that, the research team in that is focused on how to miniaturize antennas, how to put antennas in very small dimension, small casing, and how to uh, and uh, how to design a multiple antenna system. Such as some applications such as 5G and diversity system, MIMO, etc. And at that we have lots of equipment, very huge equipment. There are adequate chamber to measure the antenna. There are the edge parameter measurement and the 3D near field, far field scanner. A very big one in France. So the main content of this of the talk today is about antennas. Um, First of all, I would like to present you some definition, some characteristic about antennas. In general, the antennas have have a three main factor: the efficiency, the size, and the bandwidth. Um, if we try to decrease the size, we need to pay off on the efficiencies and bandwidth. I mean, the efficiency. When we decrease the dimension, we have the lower efficiency and lower bandwidth. So if we like to increase the bandwidth, we need to pay off on efficiency, lower efficiency, or we try to make antenna task bigger, slightly bigger. So it's very then there a relation between the efficiency, size, and bandwidth when we design on antenna. So we need to balance them. We try to have acceptable size, acceptable efficiency, and enough bandwidth for the antennas. This is a conventional idea, but for some specific application, we need to add two more feature. This name is polarization and directivities. So I would like to try to talk more detail about this some feature in this slide. First of all, is the bandwidth. What is the bandwidth of antennas? The bandwidth of antenna is defined by the reflection coefficient. It means when you provide power from RF IC, RF chip, the power will be come to antennas and radiated in outside. However, there are very small power that reflect from antenna to the source. Okay. So they define the definition is the bandwidth of antenna is the frequency band when we have the S11 in minus in smaller than some value. The standard is for the mobile device, for the small device, the S11 is smaller than minus 6 dB is enough. And for the bigger device or some base station, minus 10 dB is you need to make the antenna work well. So the dB in the minus 10 and minus 6 dB is in the decibel. When we try to convert them into linear, it means minus 10 dB. It means they are just 10% of reflected power and 90% is transmitted power. It means all of 90% of power will be radiated outside antennas. And minus 6 dB is meaning 25% is reflected and 75% is transmit power. So about the efficiency antennas, normally we have a definition in class, the total efficiencies. That's that can calculate by using matching and the radiation loss. The matching meaning the S11, the bandwidth of antennas, and the radiation loss is depend on two main factors. The first one is the electric loss that can create by the heat on the metal part of antennas, the metal line, metal element on antennas. And the second one is the loss by the dielectric. If we use the best quality, the high quality substrate, we can reduce this one. For example, on the FR4 epoxies, they have the loss tension about 0.02, something like that. And normally for a one antenna that work well, that can usable, that need to have the total efficiency around 30% to 70%. So this is some definition about reflection coefficient and the bandwidth and the efficiency. Right now, I would like to move to polarization. It is the key keyword of the talk today. So what is the polarization? Normally, in antenna, we have two kinds of polarization. The first one is linear, the second one is circular. For the linear, you can see in the slide, this is the linear polarization. When the electric field is oscillates at the carrier frequencies, and it just on vertical or horizontal. But for the circular polarization, you can see the electrical field. The electric field is rotating in at the carrier frequencies. So the direction of this rotate of the rotation will define the characteristic of circular polarization. I mean, it can be left hand or right hand. So what is the power when we use the CB antennas? Normally, in Europe, or in Asia, they are the same of maximum radiated power is about 14 dBm, and in US, I think I find out in FCC's document, they say that it's about 20 dBm. So it's meaning we have to limit our power output power below this number. That's the ERP is effective radiated power is amount of power that's applied to halfway dipole to give same power density at the given bone. So when we design device, and we program for this device work. We need to pay attention on this point. If you use linear LP antennas, I mean LP is linear polarization, you need to use exactly this number. For example, in US, you must limit your power at 20 dBm. And in Europe or Vietnam is 14 dBm. But if you use the CB antenna at your device antennas, you can put it up 3 dB more. I mean 3 dB. I mean a double maximum rated power. So it is a key advantage of CB antennas. Okay. Another advantage of CB antenna when we use in some application, in some space application. I mean, we have a in RFThings we have a design for lacuna space and antennas that can have the device at the earth to communicate with the lacuna space CubeSat via LoRa. And we see that, and we try to study about that, and we see the advantage of CB over the LP for space is, first of all, is normally in the Earth there are the Faraday effect. There are interaction between the light and the magnetic field around Earth, and it will be effect on the LP antennas, not the CB antennas. So that's why almost of the antenna for space application is CB antennas. The second one is inter-earth. The device inter-earth is mainly using the LP. So if we use the CB, that can reduce the interference. Another advantage is the higher link reliability. I mean, for the CB, for the linear antennas, we need the TX and RX is the same orientation or same position. If we rotate it in 90 degree, the link will be the quality of communication link will be reduced. So if we use the CB, we have no risk of misalignment, and normally we communicate with satellite antennas using right-hand CB. So the antenna as the Earth need to be right-hand CB. Okay. And how about the terrestrial application? With the CB antenna, we can have a double power as the output, and then at the same time with the space application, no risk of misalignment. And then we read a lot of study of paper about the CB antennas, and there are studies who say that with antennas we can reduce the influence of the fading of the multiband effect when the communication in the indoor or in the environment have a lot of obstacle, a lot of multiband. So that can help us increase the quality of channel. So this just about the theory. Right now I will show you the measurement, the real measurement in the real environment. So to prepare for this slide, we have two tests. The one test at the LoRa 868 megahertz at the French. So for this test, we set up a gateway LoRa in here in the rooftop of the building in the campus at the Sofia Tivoli. The gateway used a dipole, and we try to move around campus with three devices. The first device is the device using the CB antennas, such as the Laguna the Laguna Space Edition, the purple one here, and two other devices we use the UCA education board that's using the linear antennas. The first UCA we placed vertical, and the second one we placed horizontal, and we try to move around and receive the error side. First on before the test, we try to fix a same place and measure and try to receive the error side two different times, and we see that the 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 result is not the same. Okay, the result is not the same because in the real environment there are lots of fading effect, there are lots of multipath effect, and the movement also. That will show you the two measurement is not the same things, not exactly the same things. So we try to measure, we will try to move around here, around campus, and there the outdoor propagation with the LoRa, and this result is shown in this slide is the RSI is the CDF, the cumulative distribution function of RSI of the receiver strength signal indicator of three type antennas. As we see that, and the horizontal antennas is the work scale, and the communication link between the horizontal antennas and the gateway is very bad. So the best case is the vertical. You can see the green line here, and the circular is a middle in the is it's not really good compared to vertical, but it is better than the horizontal. And how about indoor? Indoor, when we come to in the building and we try to measurement the same things, you can see that it's not really, the result is so not really different between three kind of antennas, but we can see in here the circularly is better than a little bit better than another horizontal and vertical. Something here is better than. So this is the test with the LoRa 868 megahertz in French, and in Vietnam we try to work on the this test just receive the RSI value, and how about the data? And in Vietnam, we try to we try to make another test that's using the LoRa 3.4 PokerChip. This is our plastic device. We just finished the prototype in last month. So what is the LoRa 2.4 PokerChip? That's have a dimension about that have the diameter about 30 millimeter and the height of 9 millimeter. If you use some coin battery, you can increase a little bit the height of the device. And normally this device is an antenna, and we put every component. There are IC of same type. The S is 12 IT in here, and another MCU, low power MCUs, the Atmel 32AP in here to program to control the whole system. We have a also a pressure sensor, the PMP to IO in the device to measure the the pressure, the air pressure, and the temperature. And at the bottom of device is using the CMOS battery. So it is some example for our mindset. The antenna on system is here. Antenna on the system at the bottom. So it is very small things, and we use the you can see in this slide they this is the CB antennas, the right hand circular polarization. So how about test? With the test we use we use a module EPI. You know EPI, the EPI in a company that provide the module of LoRa 2.4 gigahertz, and also another band. There are lots of band. There are lots of modules that provided by EPI. After it, we use EPI to connect to a circular polarization antennas, and we try to measure at the different position and different scenario. And at each position, we use two device, the RFThings device and the EPI device. You can see here the EPI, the module EPI of 2.4 GHz in this one, and there are MCU to control and to send to control this module. So at each position, we try to receive the data from this that's sent to RS. This one is RS. So we make three outdoor tests. The first outdoor test is live side with the distance is 100 meter, and the live side with the distance is 700 meter. And then another test is a non-live side when we move to a building, not move into a building, but there are building and there's some obstacle between the test and ice. So let's see. How about the result? Okay. For the test, live side test, we can see in this chart here. At each position, we try to modify the SF, the separating factor, from 5 to 10, and then to 12 at each position, and we try to measure the packet error rate of each position. And we can see here at the 100 meter with SF E5 10, we have no packet loss. So it's very good performance of the device. However, when we move to SF at F12 in here, you can see the EPI have a loss about 14%, and the RFThings have a loss about 6%. So, and then we make another test at the 700 meter, and this is live side, and we make the same thing. We change the SF separating factor, and we receive that. And from this result, we can conclude that with the CB antennas, the packet error rate is lower than the linear antennas. Okay, and how about the non-live side? Yeah, with the non-live side, there are a lot of problems. Okay, you can see here with the SF is 5, packet loss is huge. For the EPI, for the linear antennas, the packet loss it come up to 97%. Oh, it not a good communication channel. And for the RFThings, for the CB antennas, it's a 53%. So we need to train the SF to higher, to try to increase the quality of channel. And you can see here when we train the SF to 10 and 12, we have a better communication. However, in this chart we can see also with the CB antennas, the packet LoRa is lower than the linear antennas. So this is a test outdoor, and how about test indoor? For the indoor test, we test in the building of University Information Technology, and the test is put in the 6th floors, and we try to measure in the RS at the 10th floor. It's the same thing with the test outdoor. We use 2 modules, one linear antennas and another one is CB antennas. And we try to at this position we try to change the SF, the spring factor of LoRa, and we measure the packet error rate. It's same thing. When we increase the SF, we can reduce the packet error rate, and with the CB antenna, we have a better result compared with the linear antennas. So it's all about the test to show you that if we use the CB antennas, we can improve the quality of communication channel. That is a huge advantage of CB antennas. So the CB antenna have some disadvantages, such as first of all, to design an antennas with the circular polarization is not easy and very hard, because we need to make sure that work at the good frequency, that have an axial ratio at a small axial ratio in this frequency, and the efficiency and the efficiency of antenna also. And then the second one, disadvantage is normally the dimension of antennas, that is CP, that is a circular operation, is a bigger than linear. So it's very hard to make a miniature antennas with CP. So that's all of my talk today. And one more thing, I some product about some product of RFThings. You can check in the website of RFThings. You can see they are the Lacuna Sphere antenna version that's using for the design kit to communicate with the Lacuna CubeSat via LoRa. This one is this purple one is the limited edition of Lacuna. And the black one is the RFThings version. We have also two things. The first, two more things. The first one is the DK, the design kit of Lacuna design kit that will be available in the end of this year. That is that kit will become can be communicate with the Lacuna Sphere CubeSat, and we provide you the kit, the antenna that integrated on, and the casing also. And this one, this casing is IP 65, I think 65 that we test. And another one is the PokerChip, the LoRa 2.4 PokerChip. That's also available in the end of the year. Okay, if you need more information, please go to the RFThings.com.vn to more details. Thank you.
Hey, thank you. No, that was a fantastic presentation, and I sincerely appreciate you coming in. I know we're kind of way out of your time zone, but coming in and presenting for us. Do you mind taking a few questions from the community?
Yeah. Yeah.
I know a lot of what you spoke about was pretty advanced, and I'd love it if you could just field a few questions from us before
Sure.
you have to jump off the call.
Okay. For sure. Yes. I waited
And
for question.
okay, and so if anyone on the call, I mean, if you're new to Helium Hacks, feel free to just unmute and kind of jump in on voice and go ahead and ask away if you have a question for this.
Yeah, I have a quick question. How well does the CP antenna work with a linear antenna if your device is linear?
The wing view antenna is what is? Sorry.
If you have a CP antenna and a linear antenna,
Yeah.
how well do they talk together?
It's nice. It's nice question. No, normally, first of all, it depends on the antennas. Okay. And if we use the CB and the linear antenna work together, it depends on the orientation of your device. Okay. If the antenna, the linear antenna with the same direction with the TX and I mean TX and RX antenna is the same alignment. I mean same orientation, position. I think the LP will be provide a good a better result. However, if you have some problem such as the misalignment, the CB will be provide a better result. Okay, it's your question, right?
And are we primarily talking about the circular being on the node orientation and the linear being on the I guess the gateway or the other end, or can you clarify that just a little bit?
I mean the orientation is meaning when you put the antenna linear like that for TX and RS, it will be a best communication. However, we change the direction of the TX or RS. The linking the communication link will be reduced. The quality of linking up, the quality of communication will be reduced. And for the CB antennas, you can put every direction you want. So we have no problem with the misalignment.
So a lot of the Helium hotspots and installations that folks have done leverage linear antennas, typically in a vertical polarization. When we're thinking about building end nodes for this network, am I understanding it correctly that in your findings, like if we were designing a mobile end node, say like a dog collar, perhaps the preferred approach is to use a circular polarized antenna as opposed to a linear antenna in those scenarios?
Yeah. Could you repeat your question, please?
Sure. So
Yeah.
an end node device that is, in other words, not stationary or not fixed.
Yeah, enough. Yeah.
It's preferred to use a circular polarized antenna just for the sort of the issue of orientation.
Yes.
Okay. Do you find it's also valuable to create gateways using circular polarized antennas?
Yeah, you know,
sort of.
Yeah. Yes, it's very nice idea. You know, at the cellular network, it is the mobile station, mobile phone station. So it's the cellular. Every antenna of the cellular base station is using the CB antennas. Yeah, you know, because of we cannot normally we can because of the antenna, the CB antennas is hard to design, it's hard to make a small antennas, so it also hard to put it in a mobile device. So that's why not every but almost mobile device starts using the linear antennas. To solve this problem, the people do that. They make a CB antenna at the space station, at the gateways. So that can solve this problem. So this is a very good idea. So almost of antennas using for base station in the cellular network is using the CB antennas. But for the LoRa one, for the LoRa, I I have to see a lot of gateway, but I think there are no gateway using the CB antenna as antennas. Yeah, it's your question. Okay.
Yeah. Yes, thanks.
Thank you for your question.
And those numbers were really fantastic. I mean, comparing the linear to the circular that you were showing, I mean, that was almost double.
Yes,
double
but sorry, but I need to highlight that for not to use the CB antenna. It's not simple, you know, because to make the circularly polarization with some specific geometry. So it's very hard to make a small antennas. So yes, it have a lot of advantage, but it have also inconvenience. Okay. Okay. So some more question.
Yeah, well, I actually have another question.
Yeah.
Will you be providing, or is RFThings, are they offering something that could be used for gateways rather than end nodes? Also, I love the term PokerChip. I think that's fantastic. But for a circular antenna solution for, I guess, a hotspot or a gateway on LoRaWAN rather than on the end node.
Yeah. As the suggestion, yes, I think the CB antennas is better when we use it with the gateway. Yes, but you know, at this moment at this moment I don't see the the gateway with the CB and the LoRa gateway with the CB antenna. So I don't know. So
Okay.
that's why I provide a CB antenna on the another. Okay. And you can see the dimension of whole device, the antenna and the circuit. It's not very big. It's very small. It's just 30 millimeter. I think it's small.
And I believe we have some community members here who have these Lacuna Space antennas in hand. I believe I see a couple on call. If anyone wanted to jump in and just quickly talk about their experience or at least their interaction with them, like the out of boxing.
And just one more thing, I would like to show you this one. You know, you see it? This one. That's in the design kit of Lacuna Space. That have the antennas, the circularly antennas put on top. Okay. It's the cabin also.
That's cool. Are you offering those in the US 915 frequencies or just in the?
Yes, all of frequency band. Normally we have you have a three frequency band. The first one is in the Europe. 868 megahertz. Second one is US, the 915, and then the AS, the Asia, is about 923, I think. Yeah.
Okay, thanks.
But if you need some specific frequency, just make a notification for us. We can tune it for your requirement.
Cool.
Okay.
There's a question that we have in chat. Is there a convention on right hand versus left hand orientation?
The convention, sorry.
Is it better to do right hand versus left hand orientation? Is there a difference? Is one better than the other?
Okay. It's your it's a very good question. Okay, if you have the text in right hand, you should use the text the eyes in right hand. If you use the the left hand for the eyes, you can have the very fast, very work communication. You know, the right hand communicate with the right hand, but the right hand cannot communicate with the left hand. And yes, I have a very good experiment in when I work with a company who make the drone, the racing drone. And normally for the racing drone, we have just eight frequency channel. Okay, so for the racing, enough. There's some racing with the 10 or more than 10. So what they do is they use at the channel 1, they use the TXLS is right hand for the people 1 and for the person 1, and another person they use the same frequency but the left hand antennas. So you know that if you use the left hand and right hand to communication together, you have a 30 dB of loss. You know, so you cannot. I think don't use the left hand to communicate with the right hand.
So that's a real life case where the right hand doesn't know what the left hand is doing.
And I think it's the same thing, but the geometry of antenna there's some modification on the geometry antennas. Just mirror it, we can have a right hand, and the right hand just mirror the right hand, we can have the left hand antennas. But the performance is the same.
That's great. Thanks.
Thank you.
Can I ask a question? Sorry, on the antenna size, do you think the smallest size we can do the circular is the Lacuna antenna you've designed, which is about 17 centimeters, right? Is that the smallest you can do, or can you go smaller?
Okay. It's also an innovation. As I mentioned in the first slide of antennas, we have five factor. So if we reduce the dimension, we need to pay on the efficiency again. Mm-hmm. And for the RFThings product, we are developing smaller than antennas. But when I test with the space, with the Lacuna space CubeSat, we see that the antennas is not very the efficiency is not higher than I don't know, but it's a little bit lower than the Lacuna version. this one, the purple one. So for the antenna, what we do, the dimension is around 14 millimeter by 40 millimeter by 20 millimeter, I think. It's a grip, like grip.
Okay.
Just wait a minute. I will try it and show you right now.
Ooh. Cool. Live demo.
Interesting.
One thing that you had mentioned I wanted to ask about was something that comes up a lot in, I guess, urban environments where you have basically your radio frequency bouncing around buildings and whatnot. And the numbers that you were showing there on how the circular handles that much better. Could you speak on that for just a sec?
Sorry, could you repeat it? Because I just go out to find for just.
Yeah, he left the room for a bit, Travis.
Oh.
Might have to repeat the question.
My apologies there. I was just asking about in urban environments where you're getting reflection and you're getting RF, kind of bouncing around buildings, the numbers that you were showing on circular versus linear on the performance there. Could you just touch on that just for a second?
Is this you like to mention the which test, the first test or the second or the second test or
No, I think it may have been the first test actually, not the indoor.
Okay, the outdoor. Right?
I thought there was a slide that was talking about.
This one?
No, keep going. Let's see.
I think.
Yeah, I think. Yeah, one more actually, I believe is the slide I'm referring to. One more slide.
One more. Sorry. Okay. Sorry.
I believe.
No.
We're talking about the multipathing here.
Multipathing. Yeah. As as we read in the scientific research article, research paper, and a lot of papers show the CPU could be reduce the fading, the multipath effect. Yeah.
I was just wondering if you could give some of our listeners here just a quick overview of what multipath influence is and that interference on in this environment. Okay. I'm sorry, that's asking a lot. And I know that whenever we talk about antennas and radio frequencies, it's a very difficult talk because there are so many factors that come into play. And so when someone just says, hey, how do I make this better? You're like, well, yeah, well, you got about 8 hours. We can sit down and chat, but multipathing, I believe, is a big influence, especially in urban environments.
And, exactly. Normally in urban or in indoor, in deep indoor,
right.
There are lots of multipath and a lot of fading. It will be decrease your communication link. I when I work in my PhD, I have a test. I have made a test pen to measure the environment factor. It's meaning the multipath, the fading on the environment, and we see that the receiver power is not constant like that, and there are lots of defay. So at this point, the receive power is very, very small. So I think if it's smaller than the sensitivity of the IC, of the RF chip, we can receive nothing. So
Very cool.
Yeah. I mean, if I could speak quickly, Travis, can you hear me?
Yes, of course, please.
Yeah. Hi, Lewis. Really
so,
enjoyed it. I a little bit over my head, but at the same time, I learned something every time. And thank you, Travis, for pulling this together. I'm just thinking about my own application in an urban area, Lewis. And so this is relevant to me with some of my customers who are not very technologically savvy when it comes to LoRa WAN and gateways. We're setting up in multiple buildings and outside, indoor and outside. So a multipath, type of RF things could be very helpful, because the signals we'll have 3 gateways on a campus basically. And there's a lot of different height buildings, and there's on the grounds, different heights and distances basically. So I don't know, this seems to me like this could solve a problem if we have a problem with what we implement. Travis, would you want to comment on that a little bit too?
No. No, I'm sorry. I think that this technology is very interesting. If you look at the graphs there, George, the numbers, I don't know, seem to speak for themselves as far as circular versus versus linear. Keep going, Juan. Just your bar charts over there.
Bar chart.
But it's for your use cases or your field,
normally in lab side, the fading, the multipath, it's not really impact a lot on the lab side. So I think this graph is your
Can I have a question?
Yes, please.
Those measurements, they assume that you have circularly polarized antennas on both ends, both the node and the gateway, right?
Sorry for this scenario, right?
Yeah, your measurement scenario, they have circularly polarized antennas on both the end node and the gateway.
No, normally the gateway is the CB antennas, yes. And for the TX, for the RX, we use the 2 kind of antennas: the linear in this one, and the blue one, and in the blue one, green one, and another. In our PokerChip is the black one. The PokerChip is
But my idea and also question is that you get the most benefit when you have CP antennas on both ends, right?
Yeah.
In this scenario, I mean, because it's not that viable to have a CP antenna on every kind of node. It's mostly when you have one that is moving, which we established earlier. So would you consider having a gateway because you have a lot more leeway there to put more antennas? Would you consider to have a gateway that has antenna selection and has both circularly polarized and linearly polarized one?
Yeah, it's nice.
Would this benefit you in any way, and how much, if you can say that?
How much for the antenna or sorry, I think your idea is nice. We can using pro antenna in the gateway. We can using the diversity to select which one.
Yeah, there is some kind of diversity game. Would there be one, and maybe it will be worth it, maybe not. Have you investigated this? Or do you see it as something that could be beneficial, or you just use the circularly polarized antenna and whatever gain you get, you're happy with? I mean, that's what I'm asking.
Yeah. I think it's a very nice solution, but I need to check it.
Okay, so you haven't investigated it. You mean that's what I wanted to know.
Sorry,
You haven't made a test bed for this case. You have no investigation or measurements on it.
Up to now we have no measurement for this one. But
Okay.
I think we can do it because I have a rack gateway in my universities, and they have two
Cool.
antennas. They have I think I have a diversity antennas, and I think I try to first I try to replace. Normally the antenna of rack gateway is linear. I think I try to replace one linear to the CB. It's, it can be it could be test. I think I would
Yeah, yeah.
I think
Technically, you have.
yeah. I think I will test this and maybe we will show I will show you the result. Right?
Well,
I
yeah,
think
because this would be interesting to know if it would be
yeah
worth it to design a gateway that has both linear and circular polarized antennas in order to have some diversity or antenna selection.
yeah yeah. It's an idea.
Because depending on the use case and what the end node is, you might be better suited using one or the other. So might be something to consider.
And one, I think I have one more suggestion. As I talk in the slide, there are normally the five factor of antennas: the size, the efficiency, the bandwidth, the CB, the polarization, and another one is the direction. And um, uh, I think uh, you can use the CB and linear, the two type antenna on the gateway, and also the omnidirectional and the directional in the gateway. Um, what is omnidirectional? Omnidirectional is like the PokerChip that can vary on of direction, but the directional is just like Laguna's Bay version. It just focus on some direction. So if if we can make some gateway that have the directional antennas, the linear, the omnidirectional antennas, and the CV and then the LP also, I think it's really it could be a very nice idea. With the directional antennas, the gain is very high, and that's we focus on some direction. And we have a study, we have a paper that's submitted by ourselves, the team of RFThings. The paper shows that if you use the directional antennas, you can reduce a lot of effect, a lot of fading and the multiply effects. The directional one.
Okay.
So
That makes sense.
I think if
Especially
you
if it's
try to
beautiful.
put another directional antennas, it's very good idea.
And Luis, if just to kind of point this out, if you need more real-world 915 megahertz testing, I think everyone here on this call would be more than willing to do some field testing with your poker chips or with your equipment. So,
Yeah.
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 this is very, very interesting technology.
Yeah,
Yeah.
technically it's illegal to do that where I live, but I can do it, right?
I didn't hear anything. I didn't hear anything there. Yeah.
Okay. It's not that important. You can go on.
No. I just meant, yeah, no one heard anything there.
Oh, okay.
No, but this was fantastic. I want to kind of respect everyone's time. I know we kind of try to keep this down to, a happy hour. I know this has gone on for a happy 3 hours before in the past, but just wanted to let anyone know that thank you very much for joining, and thank you very much for presenting tonight. This has been fantastic. I don't want to cut the session short though, and if you, because I know, what is it, midnight your time right now?
Yeah, and right now in Vietnam, I don't know. It's just 6 o'clock.
Jesus.
Okay.
It's like 12 hours from now, Travis.
Yeah.
Okay. But I know you have been very generous with your time, and I don't want to keep you up where you're groggy in the morning. But you know, if we want to continue this on, it is absolutely on your plate here. And you know, you can, like I say, you can talk about antennas for hours and hours and hours, and still have a whole lot to cover. But this is fantastic. And what I would like to do is put the links from this talk up on Discord in the events channel.
Yeah.
And so if anyone wants to, anyone has any questions, I'll throw those up over there. And then I will get a copy of this talk up on our YouTube, and for anyone who missed it. Yeah.
Okay. Okay, it's okay for me. Nice.
Thank you, Louis. Thank you, Travis.
Thank you.
You.
Okay.
That's very good. Thank you.
Yeah.
And I wasn't trying to completely cut off the call there. I was just saying if you need to go, if it's midnight there, you know, please don't let us tie you up. But I've got about 1 million more questions, but I can hold off. I'm kind of a fan of antennas.
It's 7 o'clock in the morning there.
6 o'clock in Vietnam, isn't it?
Yeah,
6 a.m.
Oh,
6 a.m.
Did you have your coffee already, Louis?
I think so. I will come back to my bed. And just this is the antennas, the new, the smaller one. You can see. Very smaller. But
Is that the PokerChip?
Okay,
Sorry?
that looks nice. Okay, that's way small enough for
You
me.
put it in front of the camera and
this
keep it
one?
still. Yeah, and keep it still. Yeah.
Yeah.
What's the frequency? What's the frequency for that one?
You know, in the antennas, the frequency in we can provide any frequencies.
Okay, yeah, we just lose. But what's the target?
For this one is for AS10 900.
Okay.
900. And you can see you can try to compare with the Lacuna version. Let's see. But it's a little bit not low profile. It's a little bit higher. And then if you see it's not very good, so that's why we don't put this. We need to improve it before selling. So it's not very good compared with when compared with the Lacuna one.
I saw in one of your data slides or one of your slide sheets, like an 8-chamber picture. And do you have 8-chamber like data results for these Omnis?
You mean any chamber, right?
Yes.
Yeah. Normally we for the measurement for the antenna measurement on the device, we use the prototype is measurement by in the anechoic chamber. Yes. The far field radiation pattern is measured in the anechoic chamber. However, when the antenna is fixed, I mean some parameter in the antenna is fixed, we just use the nano VNA, you know, the small things, small device to measure the S11 for the mass. I mean for the production. When we fabricate an antenna, we follow the dimension of the antenna that's measure it on the chamber, and we make the same thing, and we measure, we project it with the nano VNA. Nano VNA is the machine a little in small machine to measure the S11.
And the nano VNA is something that we've discussed on this call before. And that's something that I know a number of people have in hand now.
Yeah.
And there's it's a cool little device. I think both those and the N1201 SAs a lot of folks are using those in hand right now.
It is a very useful device.
Infinitely, yes. And I tell everyone this. If you're deploying antennas and you're not using a VNA, then you're doing it absolutely wrong. Just for a variety of reasons. But
yeah.
Very cool.
Okay.
Well, do we have any more questions? Well, we have this wealth of knowledge online right now. And like I say, thank you very much for joining us on the Helium Hacks Happy Hour today. Thank you very much for speaking. And will these slides be available? Can we put these up onto our Discord channel so people can reference them?
Do you have a PokerChip available? I mean, where you're at now?
Right now, I think I think I will come back to bed. No, yeah, I had a course at my university in the afternoon, so for the morning I think I freeze.
I was just curious about the size of the PokerChip.
PokerChip, okay. This one. This one?
Yes. Oh, I see the dimensions right there. 30 by 30 by 9. Okay.
Okay, 30 by 9.
I guess I was sleeping.
So about the size of a...
Don't say it, Travis. I don't know where you gamble, but where I gamble,
Okay, Eddie's just messing with me. And, okay, well, I'll like I say, I'll let this conversation go on if there are more questions. But please unmute your mic and jump in here while we have this opportunity. If you have a question.
Okay.
I have a question. Hey, Louis, this is Randall.
Hey.
In 5 or 10 more years, how much smaller do you think you can make your antennas?
How far kilometer? You mean the distance, right?
The size. In the future, what do you think is a size you can make even smaller, like half? Or...
Don't ask me about the size. You know, we in the antennas. We need to pay attention in the 3 main factor. We reduce the size. Yes, I can. First, the efficiency of antennas it's not very good and not very acceptable for I don't know, but you can see a lot of small antenna, but I think the efficiency of antenna is not good. So about the small size antennas, I don't know. I have no idea.
Man, Randall, eat your Brussels sprouts and live long enough, and everyone will find out. So,
maybe let me ask the question another way. From year to year, when you're making the model, how much percentage-wise smaller do you get each year or each couple years?
You like to talk about the how is the name of the guys? The law, the
Moore's law for antennas.
Okay,
for antennas, right? Yeah.
Doesn't apply.
So I will tell the smaller than this one after 2 years, right? No, for the antenna there are limit. Yeah, there are limit. We cannot.
Hold on, Randall. To address this, there is a PCB antenna reference kit that Texas Instruments makes that I would highly recommend you look at if you want that question answered. But
Okay,
otherwise,
link.
it's so yeah. Well, Texas Instruments PCB antenna kit. I don't know. I don't have the link on hand, but that's what it is. You'll find it. It'll come up directly. But I think that is a good, at least, reference point for dealing with questions like this, because when you're dealing with radio frequency, it has to do with wavelengths, and so you're dealing, with one, half quarter, et cetera, wavelengths, depending upon what frequency you're operating on, and so that is kind of inherently, built into what we're talking about here.
Yeah.
It's more related to physics than electronics at this point, I think.
Yeah. Gotcha.
There the limit. Its name is true limit or horizontal limit, and this limit that provide a curve, and the x the y axis is the dimension, and the x axis is the efficiency of the gain. As I remember that. And the limit is, they are the theory limit, so we cannot pass the limit. So with the small antenna, we have a small efficiency. If we have a big antenna, we have big efficiencies. So the antennas, the dimension antenna, it depends on the wavelength. so we cannot. I don't know, in the future maybe there's some technologies for some. Maybe some material with the higher conductivity, we can reduce the antennas. But
We're gonna have hover LoRa and boards in the future. I can feel it.
Yeah, maybe. The ceramic one, the ceramic antennas. That's using the ceramic as the material that can reduce the size, because of it have a high dielectric permittivity, so it can reduce the size. But I think I think for the BCB antennas we cannot. But maybe in the future, someone who find out a material, a good material, we can reduce.
Well, man, this has been absolutely fantastic. If we're going to be speculating about the future, I mean, we could go on all night. We're 20 minutes over time right now, so I'm going to let Luis go. And thank you very much for speaking tonight. This has been fantastic. And I'll follow up with you and get you a link to the video and links that have been discussed here in group chat.
Yeah.
But thank you, and thank you all for attending yet another Helium Hacks Happy Hour, and we'll see you again next week.
Thank you for your time, everyone.
Thank you, Lewis. Thank you, Travis.
Yeah.
Thank you very much.
Yeah.
Take care, folks. Bye.
Thank you. Bye.